right, we need to keep going so you guys do not end up with weekend homework. So let's focus, lock in here. All right, so solving exponential and log equations. Our key thing that we must remember is that the inverse operation of an exponential expression is a, anybody know? What's the inverse of exponential? Is a log. And the inverse of a logarithmic expression, inverse of a log, is a exponential. Oh, sorry. So, as far as solving these equations go, we are going to be doing the same things we've been doing on solving other equations. But we have a new tool where if we run into a log or an exponential, we will be able to reverse those as well. You haven't seen those equations yet because nobody's taught you how to solve that type. But some of the same pieces are going to be the same. So this is important right here. You need to always check your answers on these problems. Because sometimes these problems can produce extraneous solutions, which means that you did everything right, but the answer is not correct. So you always want to check your answers. I know your teachers have been telling you to check your answers like since you were little. And like in Math 1, you could plug it back in to check, and nobody ever does because it's extra work and you don't want to try, right? Like you don't want to do that. But you always need to check your answers on these because sometimes you can do everything right and then that answer still doesn't work for these. It's because of the nature of what you're doing here. Your logarithms can't have negatives on the inside of the logarithm, so you can get a negative answer, but you can't have negatives on the inside of a log, so you have to check for these. So you can either plug your answer back into the original equation and make sure you get the same value on each side, which is what you've been taught since Math 1. Just plug that number back in. Or we could use Desmos to check by graphing them, right, like we have done on other problems. So you always want to check these, and I will try to practice what I'm preaching here by checking the ones that we do here. So let's look at a few different problems. So you're going to run into several different types of problems. These three examples are exponential equations because we have a number being raised to a power and we got a variable up there. But these are a specific type of exponential equation that's really not all that bad to do. Because what do you notice about the exponential equation on both sides of this equation here? These numbers right here, these threes are the same, right? So, for me to get 3 to something equals 3 to something here, our exponents have to be the same, right? Essentially what you can think about doing here is if I want to undo that base of that exponent, right, there's that base of that exponent. What you're doing is you're doing a log with a base of 3, and it cancels this out. And then you do a log with a base of 3 here, and it cancels that 3 out. So if the bases are the same, you're really just dropping the bases. You're getting 3x plus 3 equals 4. And then we just have a two-step equation to solve. So Hunter, what would we do to finish solving that equation? Good. We'll subtract 3. So that will give us 3x equals 1. And then what will we do last, Hunter? Divide by 3. So x is just going to equal 1/3. I'm just going to leave that a fraction right there. And so I'm going to double check this. with Desmos because it is probably going to be your preferred method. Why is that not split screen like it's supposed to? Okay, there we go. So if I do f of x equals the left side, 3 to the... Desmos does something weird here. If I'm trying to put 3x plus 3, it won't put it in the exponent, and it's aggravating. To do that, put some parentheses around your exponent, 3x plus 3, and it'll keep everything up there together. So that's going to be a little glitch in Desmos you're going to run into. It's going to try to jump down from the exponent before you want it to. So that's how you'll type in the left side. The right side is going to be 3 to the 4th. Now, one of the bad things about using Desmos for this is that a lot of times it is hard to see where these cross. In this particular case, 3 to the 4th power is a really big number, so you got to go way up here. You want to be careful when you're looking at this. Zoom in a little bit more, because see how those two dots are so close to each other? You may accidentally click on the y-intercept here instead of clicking on the place where they actually cross. So we're getting 0.33333. That is 1/3. So we can see that we did that correctly. Okay, questions there? All right, you want to check every single one. There's not a lot of them that have extraneous solutions, but it happens. So you want to be very diligent to check. Let's look at 2. It's similar. I've got the bases are the same. So if the bases are the same, I'm going to log 3 both sides. I'm just going to be left with the exponent. 3k minus 2 is going to equal negative 3k plus 2. Now, I've got k's on both sides this time. So what have I got to do to solve this? What? I've got to combine them, but I can't just put them together because they're on opposite sides. So I need to, like, move one to the other side. So I'll plus the 3k, but, oh, what happens here? It's not just k. Negative 3 plus 3 is 0. And 0 times anything is 0. So I got like 0k, but 0k is 0. Cancels on both sides. So I've got negative 2 equals 2. And does negative 2 equal 2? That's not true, right? What do I say about this equation if I get something like this? We can't because there's not a variable over here in this case. If I had a k left, that's what I'd do. This is a no solution. Let's graph this one to see what it looks like on Desmos. Because while I definitely want you guys to be able to solve these by hand, that is the best way and, you know, my goal. If you can't, you could rely on Desmos. Make sure you type that k in as a x because it doesn't like k's. If I graph these, I just have these two exponentials right here. They're decaying. It looks like they probably crossed somewhere, but if I click on it, like I don't really have, I got like a gray dot over here, but if I zoom in there, it just, the gray dot's not really doing much. And like if I zoom in right here, it looks like those two are touching, but if I zoom in enough, are they actually touching? They are not. So these two graphs don't cross at all. So you don't have a solution for that one. Okay. Let's look at 3. For that one, you've got the bases are the same. If I log base 5 both sides, I just basically am left with my exponents, 3n plus 3. equals 3n plus 3. In this case, I've got n's on both sides, so I need to move one to the other side. It really doesn't matter which one you move here. I kind of like to move this one. I like to add that 3n because it avoids negatives, but some of you may want to subtract this 3n. Either one is fine. So I've got 3 equals 6n plus 3. What should I do next? I'm going to subtract that 3. What's 3 minus 3? 0. A lot of kids won't say no solution at this point, but it's okay. You still have an n. No solutions for when your variable cancels out. You still have an n. All right, I got one more step. I got to get rid of that 6. Caden, how do I get rid of that 6? Divide. Good. So, n equals 0. That is an answer. That is not a no solution. That is an answer. So, if we graph that one to see what it looks like. Over here, I will have 5 to the negative 3n, or x, plus 3. And over here, I will have 5 to the 3x plus 3. And I'm going to hit the house button. It looks like they're not going to cross. They do cross, don't they? The problem with these is that sometimes the numbers are so big. So I zoomed way out, and if I click right here, it's 0, 125. Let's zoom in to make sure they are like actually kind of, if we can see. Sometimes it's tough. I don't know if I'm going to be able to see that one. I'm going to hit the house. Let me try something different. If these cross, I really don't need to, if they cross, they're crossing in the middle, right there at 0, right? I really don't need to see, I don't need this to be any wider. I just need it to be taller. So here's an option whenever you got a graph that's hard to see. If you hit the wrench over here, you can change just the x-axis or just the y-axis. All we really care about changing is the y-axis here. So if I make that like 200, then now I can sort of see a little better. They do actually cross a little bit there for that. In fact, if I make my x's smaller, if I make this like negative 1 to 1, I bet we'll be able to see that they cross for sure. There, now it looks like they actually cross, right? So you have to play around with that sometimes. These are a little harder to solve on Desmos because whenever you solve these on Desmos, the graphs are crazier because exponentials and logs have, like, they grow really quickly. So they're a little harder to solve on Desmos than like the absolute values that we were looking at before. But it works just the same. Okay, moving on. All right, let's look at what to do when we do not have the same bases on both sides. So the ones we were just looking at had the same bases. If I look at like example 4, I've got 11 to the nth power equals 44. And this is not one I can just guess at because 11 to the first power would be 11. 11 to the second power would be 121. So like it's not a whole number. It's something between 1 and 2. And I could go over to Desmos and we could type in numbers like Carson and Jose did the other day till you got exactly 19 on that one problem. But that would take forever, right? So we want to solve this using the methods that we know. I need to get rid of the 11. You might want to say that we should divide by 11. But is this 11 times n? It is not. We also are not going to do a root. Because roots get rid of the exponent. Like if I have x squared, I can use the root to get rid of the square. So it's not roots. What is the inverse of an exponential? a log. So to get rid of the base right here, we have to use a log. And the base of that exponent is 11, so we are going to use a log with a base of 11. So we'll do that on this side, and it'll cancel out. We'll do that over here as well. And so we get n equals log base 11 of 44. And we can't do that by hand. We are going to type it into Desmos to make sure. And so we're just going to type in log base 11 of 44, and I get 1.578, 129, and so on. So keep at least 3 decimal places for me, so 1.578. Hector, while you up, will you mind shutting that door too? Thank you. Okay? And in fact, on this one, you need to check your answers, but it's probably easier on this one just to plug that number in. You can just like copy and paste through 11 to that power. And I'm getting 44 point. They do have like an 04, like a bunch of O's in the 4. That's because logs have to be rounded. They go on forever. But this is essentially the same, so that you've done this correctly. In fact, that'll probably be a lot easier than the graph for that. Okay, questions? All right, so looking at the next one, for that, who could tell me what to do on the next problem? Okay, we're going to do a log with a base of 15 here. That'll cancel out that 15. If I do that to one side, also have to do it to the other. Perfect. Right, and then all we have to do is go type that into Desmos to get our decimal for that. And we're getting 1.70054. I'm going to round that to 1.701 for that. And there's my answer. Now, definitely if you use that, like, if you use the rounded version of that answer to check, if I do 15 to the 1.701, it's going to be close but not exact. If you use if you like copy and paste the whole thing, you'll get much closer. It's going to be off just a hair because these are irrational numbers that go on forever. And even this number that they're giving you right here, the calculator has rounded it off. It actually goes on further than that. But it'll be plenty close enough for what we need to do in this class. Okay, so let's look at ones that are a little bit tougher. Okay, so I've got example 6. I've got 2 to the k minus 4 minus 1 equals 8. So I've got more things going on in this equation. You solve it just like you would solve a regular equation. So if I'm trying to solve for that k right there, I want to start furthest away from that k. What do I need to try to get rid of first, Cannon? Good. And what do I do to get rid of it? Add 1. So it's a lot of the same things that we've done on other equations, right? So I've got 2 to the k minus 4 equals 9. And now I'm trying to get to the k. I can't mess with that 4 because it's up there in the exponent, right? What have I got to get rid of next? I got to get rid of that base of the exponent. And Joey, what do I do to get rid of a base of an exponent? Log with that same base. So log base 2 right here. We'll cancel that out. But if I do that to one side, I've got to do it to the other. So over here, I will just have k minus 4. Right here, I'm going to have log base 2 of 9. And it makes it hard to go forward with that. Technically, you could and wait till the end to type it in. But log base 2 of 9 is a number. I can type that into Desmos and get a decimal for it. So if I just go over here and type in log base 2 of 9, I get 3.169925. Keep that number in your calculator because you don't want to round it off till you're done. But I could write down the rounded version, although I forgot it. What was it? 3.169925. Why is my brain not holding numbers better than that? 1.69925. You want to wait till the very end of the problem to round your answer on these, because if you round too early, it can cause you to be off by more than the 3 decimal places. And then we just need to add the 4. Well, actually, that's pretty easy there, right? We just got 7.16. In fact, 9925. If you want, I need you to keep at least 3 decimal places. Like, I would be upset if you rounded this to 1.7. I want at least 3 decimal places. But this is not the easiest rounding in the world right here, because you got a 99 where you're trying to round. So if you just want to keep extra places, that's fine too, to avoid difficult rounding. But if we are going to round that, let's think about it. 7.169925. If I am trying to round this off right here, I usually find that somehow we've made it nearly to adulthood and don't know how to round. Especially in this case, it's a little trickier. What is that going to be if you round it to 3 decimal places? 170. Because it's rounding. Think about, like, that 9 means I got to round this up. Normally we just round that next number up, but that is already a 9. So we got to round it to a 10. Think about the whole number. That means 169 has to become 170, right, for that. So if you have to round it, it looks like this. You can just keep extra places. It's okay with me too. All right, try that next one on your own. See what you can do with that next one on your own. If you can do it, you should be able to do any of the exponential problems that I'm going to throw at you. See if we can get zoomed in. Good here. I believe everything looks good for what Emma has. So your first step on this one, you're going to subtract that 7. So you should get 14 to the 10m minus 3 equals 65. Then to get rid of that 14, you got to log 14 on both sides. Now, I've seen most everybody do that. That's great. You're not dividing by 14. Kids want to divide by 14, and that will not work. So you do log base 14 of 65. You're just typing that into Desmos and getting this big decimal. So it should be 1.58177, and it does keep on going there. For that, once you get to that point, you should have a relatively simple equation to solve from there. So you just have to add the 3, and you get 4.58177, and divide by 10. And then if you round that off, it'll be 0.458177 if you want to keep more. But that looks beautiful there. Okay, it was looking pretty good whenever we walked around. Lots of people had the right answer. And those of you that did ask questions and didn't have it were close. So, looking good. All right. So, those are for exponentials. I think my next slide here is going to have logs. So, I hate so much that Coach Wood's not here. How many of you had Coach Wood for class? You missed out because Math 1 does not have logarithms in it. This used to be Coach Wood's, one of his favorite things. Like, if he were here right now, he'd probably be walking through the hallway because somehow he was never actually in his classroom. It wasn't his planning period. There were kids in his classroom. He just wasn't there. And he would come down the hall, and if he saw that we were working on this right here, like if he looked through my door and saw this, he would stick his head in the door, and he would yell, "Drop the logs," and then he would walk off. He thought that was a funny phrase that describes something that you would need to use a bathroom pass for, and he loved to yell it out. He'd draw poop emojis on his slides during this time. It was his favorite thing. He loved making a scene so much. So if you didn't get to have Coach Woods, you missed out on some good entertainment. But in this case, if I have a natural log on both sides, what is the base for a natural log? It was weird. It's not a number, it's a letter. It's E, even though it really is a number, right? E is kind of like pi. So if I want to get rid of a natural log, then I need an exponential on both sides. So I would do e to the power. But whenever I do that, it just gets rid of the logs on both sides. So this is what Coach Wood would always call dropping the logs, right? We just drop the logs because there's one on each side. So I've got 5k minus 7 equals k plus 9. And you're going to solve this equation. This equation has k's on both sides. So Heston, what would I have to do first here? You could. I discourage you from moving the numbers first. Because a lot of times kids move the numbers and then they can't figure out what to do with those variables. I usually tell kids to move the variables first. So we got a 5k and a 1k. Let's get those together first. It makes your path forward a little more clear after that. So which one do you want to move, the 5k or the 1k that we've got right there? Okay, so we're going to subtract that 1k to move it over to the other side. So that's going to give us 4k minus 7 equals 9. And then what would we do, Heston? Okay. And so 4k is going to equal 16. And last step, divide that 4. K equals 4. Now, the big thing for this, for extraneous solutions, is you can't have a negative inside of the log. We can't do logs of a negative number, like if you go over here to Desmos and try to type it in. Like if you were doing log of -4, it's just going to say that it's undefined. You can't do logs of negatives. So you can graph this whole thing to see where they cross. That's definitely an option. But the big thing you're looking for here is you want to make sure that when you plug this back in up here, 5 times 4 minus 7, it has to be a positive number. It cannot be 0. It cannot be negative. 5 times 4 is 20 minus 7, that's 13. Still positive, right? Same thing over here. 4 plus 9, that's positive. So this is okay. That also gives you 13. So you got natural log of 13 equals natural log of 13. Those are equal. And this right here is your answer. So you can do that instead of having to type it into Desmos, but you definitely can type it into Desmos as well. So whenever you see one like number 9, you've got logs with the same base. So as long as the bases are the same, what you're doing here is you're doing 6 to the power, which just drops those logs. So you got negative x minus 10 equals 4x minus 5. Sophia, what would we do to solve that one? Yep, I would add that x. Okay. I'm going to do them in separate steps, but you could do them in the same if you wanted to. You're just ahead there. And then we will add that 5. And so we get negative 5 equals 5x. And then what would we do? Divide by 5. And so we get negative 1 equals x. Now, I should feel a little alarmed about that negative answer, but sometimes you can have a negative answer. If I go up here and try to plug this in, I would have negative 1 minus 10 the negative negative becomes a positive, right? So that's going to give me 1 minus 10. What is 1 minus 10? Negative 9. Can I have that? Can I have log base 6 of negative 9? Cannot. And over here, I would have 4 times negative 1 minus 5. I'm going to get a negative 9 for that also. So we did everything right. Everything Sophia told me to do was correct. We didn't do anything mathematically wrong. But this answer is not working because it's giving us this here. If I go graph it, if I try to graph it in Desmos, f of x equals log base 6 of negative x minus 10. And g of x equals log base 6 of 4x minus 5. If I graph these and try to look at them, do they cross? They do not. They're not even close to crossing, right? So what I have here, the fancy word for this is called an extraneous solution. And it is the reason that I'm telling you got to check all of your answers. So this one does not actually work. And we would say that this problem has no solution. For that. So you got to be careful. You can do everything right for these and get an answer that doesn't work. So that's why you want to check your work every time. That doesn't happen when you're solving like linear equations in Math 1. Often, anyway. Or you know you've got no solution by the way it solves. You don't get extraneous solutions. So I get why no kid wants to actually check your work there. If you don't check, the only way you know that you're getting an extraneous solution here is if you check your work. Because Sophia did not mess up at all. Everything she did was mathematically correct. The problem itself has an extraneous solution. So you have to be careful with that. Okay, I'm going to skip 10 because I think we're pretty good here. You would just drop the logs and solve there. Let's go over here to these. For 11, I've got log b equals negative 2. Now that log, I'm trying to solve for b. I need to get that b right there by itself. I'm trying to solve for b. There's no base on that log. Okay, Zoe's telling me that it should be 10. Is she right? Yep, if there's not one written, it's a 10. So to get rid of the log, because I need to get rid of the log, what do I need to use? Inverse of logs are exponentials. It's only an e if like our base is e. So we're going to do 10 raised up to the power. Whatever the base of your log is the number you're using for the exponent. And that'll give us b. And right here, I've got 10 raised up to the power. So this is 10 to the negative 2. Anybody know what 10 to the negative 2 is? I bet not without Desmos. Although, I think it's 0.01. Negative exponents are like bad children. They get locked in the basement. You didn't have me for Math 1 either. That's one of my ways of teaching these. So what actually happens here is like the fraction, the 10 to the second goes to the bottom and becomes positive. And so you get 1 over 100, which is 0.01. So that's a good thing to know. Desmos will do it. Don't worry about it. Just use Desmos for it if it's confusing to you. Okay. For the sake of time, I'm going to skip 12 and go on down here to 13. That's a little bit trickier because this is pretty much the same question. Oh, I should check my work. But if I plug in 0.01, that is a positive number. Log of 0.01, like I could just type it into Desmos real quick. log of 0.01 is -2. I'm getting the right answer, so that is correct. You could graph it if you wanted. All right, let's look at 13. So if I'm trying to solve for P, I've got to get rid of my log base 3. I also have to get rid of my 4. Jose, what would I try to get rid of first? The log. Because as much as I'd like to do the 4 first, because it's easier, it's trapped on the inside of that log, right? So I got to get rid of the log first. How do I get rid of a log with a base of 3? Yep. So the thing you raised up to, right? So you're using an exponential with a base of 3. So 3 raised up to that power, 3 raised up to this power. So I get P plus 4 equals 3 squared. Well, 3 squared is easy to do, right? We know how to do that. Make sure you got 3 squared, not 2 to the 3rd. The 3 is the base of that exponent. So that is just 9 right there. And so, Jose, what's the last thing I got to do? Subtract that 4. And P equals 5. The big thing you're looking for is when you plug this back in, you cannot get 0 or a negative inside of that log. If I plug this back in, I got 5 plus 4. That is 9. That is positive. We're good to go. You can also check it by graphing it on Desmos as well for those. Okay. 14 is pretty much the same. Let's skip to 16 over here. Actually, I want you to have some time. Let's go on to 18. We can do 18. We can do them all. So, for 18, this one's got a lot of steps. Jalissa, what would I do first on number 18? Add that 10. So I got 4 log of 6 minus 3n equals 16. Okay. Jamaja, what would come next? We want to go furthest away from that end's what we're trying to get rid of, which is this 4 on the outside of the log. How do I get rid of that? We're going to divide it because it's right next to the log, which means it's multiplied by that log. So we're going to divide by that 4. So I've got log of 6 minus 3n equals 4. So both of those steps are just like regular solving equations. Now I've got to where I got to get rid of the log. Richard, this log does not have a base. So what is the base of this log? It is 10. And how do I get rid of a log with a base of 10? To the power of 10. So 10 to the power here and 10 to the power here. So I got 6 minus 3n equals 10 to the 4th. I can just do 10 to the 4th. It's going to be a pretty big number because it's 10 times 10 times 10 times 10. It is going to be 10,000. It is just a 1 with 4 zeros. There. We're almost there. I'm running out of room, so I'll skip over here. So 6 minus 3n equals 10,000. Okay, Adela, what would I do next? I'm going to subtract that 6. So I got negative 3n equals, that's going to give me 9994. And then, Sophie, what's the last thing I'm going to have to do for that one? Good. And now, somebody got their calculator. What is that? 3,331.3 repeating for that. Now, I will tell you this, these are really hard to check on Desmos because you're getting such a big number, your answer's like you gotta zoom way out. So they are hard to do. The main thing you're looking for, though, is you can't have a negative in the square root. So if I look at I'm not square root, the log. So if I look right here, if I do 6 minus 3 times negative 3, 1.3, repeating, I don't even care what number it is. I care about whether it's positive or negative. Am I going to get a positive or negative number when I plug that back in? It's going to be positive because this negative times negative will become positive, right? And I'll have 6 plus, it's going to be 999. I'll have 6 plus 9994, which is 10,000, which is a positive number, right? So you can just check by doing that, because if you graph this one, zooming out to find where they cross gets really tricky on that one. Okay, questions? Exponential equations with different bases are way harder, and we're going to save that for Monday, because you can't just log both sides. So I